thank you very much for sticking around. And maybe should I ask if there are questions just before we start, or should I just start? Okay, I'll just start. So let's take it from where we left it yesterday, so roughly at the middle of lecture 1 of what I had planned. So we have introduced the notion of Anosov representations. Let me just remind it. So we have gamma, discrete finitely generated group. We have G, a semisimple Lie group. And out of this, from the semisimple Lie group, we define delta, which was the set of simple roots, which were a set of functionals. Maybe let me draw for once. No. Yeah, that's not so bad. I changed my picture. Now I have 4 lines, and this is the maximal flat subspace of SO 2n. It's another Lie group, orthogonal group. And here, the roots are really, so if this is A, and A corresponds to diagonalizable matrices of the form 0, a big 0 here, A1, A2, minus A1, minus A2, then the roots here are, as you see in the picture, this is A1 equal to A2, and this guy here is A2 equal to 0. These are the roots in this setting. And you can, like, the diagonal are A1 equal to A2 or equal to minus A2, A2 equals 0, and A1 equals 0. This is one other example. And for what I, like, okay, yeah. Delta is the set of simple root, and we were choosing a subset, theta in delta. And we said that rho from gamma to G is theta Anosov if there exists a constant C bigger than 0 such that the alpha of mu of rho of gamma was bigger or equal than C times norm of gamma minus 1 over C for all gamma in gamma. This was the definition I left you with. Someone asked me, and I was like arguing that this was some way in which the orbit in the symmetric space resembles the intrinsic geometry in the group, or any hyperbolic structure that you can choose. Some of you afterwards asked me, why do I ask only for this inequality and not for the other? That's a very good question. And the answer is the other is automatic, because it's a group action. This you can do as exercise, to check that you have the other inequality. And the corollary of, so like one direct corollary that's easy from this definition is that theta Anosov representations are QI embedding. If you know what QI embedding means. If you don't know what that means, if you don't know, I haven't seen geometric group theory, just think that this is a way of making precise what it means to be to resembling the intrinsic geometry. But it's stronger than that, because we really avoid these walls. And another result that maybe I'll write here as a theorem that's due to Kapovich-Levi-Porti and Bocchi-Potri-Sambarino. And I really wanted to add also Bocchi-Potri and Sambarino because they proved this theorem using dynamics, which is the main topic of the conference, is that if gamma admits an Anosov representation, then gamma is word hyperbolic. And if you don't know what word hyperbolic means, think of then it doesn't contain Z2 subgroup. I mean, Z times Z, I mean, the free abelian group of rank 2 as a subgroup. In general, there are still, in general, the class of groups that admit Anosov representations is very big. Sami constructed lots of them recently. And there are still lots of open questions about which linear groups admit Anosov representation and doesn't, or do not. And yeah, if you don't know what this means, like this is good enough for our purposes. It's a weaker condition, but it's good enough. Yeah? But there is another way. So this is one perspective of dealing with Anosov representations. And another perspective that's closer to what I will need. So like, as I said the other day, is that, another theorem is that Anosov representations are open in the character variety. So this is an open subset of representation that have these nice properties that are QI embeddings, and so in particular are virtually injective, up to passing to finite index subgroup are injective and have discrete image. And so this is a subset of chi discrete and injective that's nice because it's open. Yeah? One can prove such a result either doing geometry of symmetric space or doing dynamics. I will not prove in either way because time is precious and it's running very fast. So it's running faster than one expects. But the key ingredient in some of the proofs of this openness are boundary maps, and which is something that's important for all what I'm doing later. So that's what I want to tell you. The topic on which I want to start 10 minutes in my class today. Any questions on this? So these are things that, yeah?
On the corollary, we just suppose that theta is not empty.
Huh? Yeah, yes, if theta is non-empty. Right. And maybe let me say, I want to talk now about boundary maps. And I will assume, without loss of generality from now forever, that theta is invariant under the opposition evolution. What does it mean? Let me tell you what this means. So for example, the opposition involution is a permutation of delta of the set of simple roots that depend on the group and might or not be trivial. Some groups have a trivial one, some groups have a non-trivial one, as O2n as a trivial opposition involution. And what the opposition involution does, I'll draw a picture here, is somehow the opposition involution is the function that takes a vector. I have a vector v, like a vector in my Weil chamber, and I take minus the vector in my Weil chamber. And now minus this vector also has a unique representative in this Weil chamber. And that's what this iota of v is. This is the opposition involution. Yeah? So it tells me that, I have ray pointing in this direction, and minus the ray might point in a different direction for our purposes in this fundamental domain. And this records what this is. But the point is that the Cartan projection of rho of gamma inverse is the opposition involution of the Cartan projection of rho of gamma. So being Anosov, since mu of rho of gamma is equal to I of mu of rho of gamma inverse, so the idea is that the vector that goes from associated to gamma inverse is nothing but O minus gamma O. So that's doing the inverse is like taking a minus sign on this vector, and then I bring it back to the Weil chamber for what I was doing. Then if rho is alpha Anosov, then it is also iota of alpha Anosov. And so I can assume, without loss of generality, that theta is big. Right? So because this condition, like if this is bigger than C, then you get this condition. And this will be useful to talk about boundary maps. But let's keep this there for a moment and go back. If there are no questions on this, let's go back and think let me explain you what I mean by boundary maps in the Teichmüller setting. And then I'll get back to this, which could have waited 10 minutes, but that's fine. Okay, so that you can think about this for a while I explain Teichmüller theory, and then I'm gonna get back and tell you how this is useful in iron rank. So we assume for concreteness, even this is very general, that gamma is the fundamental group of my surface. And I told you here that gamma is word hyperbolic. If you know what this means that it has a boundary. That set of rays in the Cayley graph up to being close by. If you don't know what this means, you can think of it. So the Gromov boundary of gamma is nothing but S1, which is the boundary of H2, in any chosen hyperbolic metric. I can choose any hyperbolic metric on the surface, and then I have that gamma is a subgroup of PSL2R, or gets identified with a subgroup of PSL2R, and thus acts on the boundary of H2 through this chosen hyperbolization. And so this is a compact space on which gamma acts, as in Barbara's course. This was important in Barbara's course. And the point is that if I choose two hyperbolic structures, so I have the topological universal covering of SG, which is a disk, and I have the map F, the isometry F with H2, which depends on the choice of a hyperbolic metric H1, and I have another map F2, which depends on choice of H2, still to the hyperbolic disk. And these are homeomorphisms, so this gives me a homeomorphism between these two hyperbolic disks that is very known in isometry because the metric that I'd chosen were different. So just a homeomorphism, a topological map. But this, and this map here is really non-unique. It depends on lots of choices. I could choose isometric metric with different map F that are close by. But the point is that this homeomorphism of the disks extends to what I want to call phi, which is a map from the boundary of H2 to the boundary of H2, which is gamma 1, gamma 2 equivariant. And the point is that while this homeomorphism depended on lots of choices, this map on the boundary is essentially uniquely determined up to conjugation with isometries. And so this is much better, and this is fixing for us the information about the metrics in a concise way. And this map has more property. This is Holder continuous, which makes Barbara happy because that kickstarts all the dynamics that she was doing in this setting. And it's for what it's, as I was saying, it's gamma 1, gamma 2 equivariant, and even more, it's monotone. And this will play a role for the positivity part, meaning that if I have three, this is a way of saying that this is injective and maps three positively oriented points to positively oriented points. Yeah, so this is some sort of injectivity. In this setting, it's the same as being injective, but for in more general settings, this monotonicity will play an important role, as we'll see later. Yeah? Is that okay for everyone?
Sorry, so again, the boundary map we just create by composing the homomorphisms and restricting to the boundary.
Right. The point is that you compose the homomorphism, and you show that these extend continuously to the boundary. And this is the boundary map.
And then you restrict the boundary.
And then I restrict the boundary. And the point is that the action on the disk is properly discontinuous. So I have lots of possible choices, possible gamma 1, gamma 2 equivalent choices. But the action on the boundary is ergodic, as we have seen in Barbara's course. So this is fixed once you ask it to be gamma 1, gamma 2 equivalent. In general, if I take a different representations, a different representation that's not in the Teichmüller space, so it's not discretely injective, you'll often still have boundary maps, but these are non-injective and like mess up things a lot. Yeah? More questions on this? So what about higher rank? That's what I want to talk about, right? So for my group G, what's the right replacement for the boundary of H2? I mean, now, like here, I was having two representation from between lattices in PSL2R, and so I have the boundary of gamma and the boundary of gamma, in a sense, or the boundary of H2 and the boundary of H2. And in this case, my boundary map will be slightly different because I want to understand what's the right boundary to attach to G. So like now for semi-simple G, I mean, one could try to think about the boundary at infinity of the symmetric space. X was G mod K. But as opposed to rank 1, as soon as G has higher rank, so as these non-trivial flats, you see from the fact that I have this Weil chamber as a fundamental domain, that the action of G on the boundary should not be transitive. Right? I mean, the action of G extends to an action of the boundary, but why should it be transitive? I was not transitive on unit vectors, so I should as well not be transitive on the boundary. And the point is that the visual boundary of X as a cat0 space, so the set of rays modulo parallelism, is stratified in G orbits, and any G orbit is a flag manifold. Which I call this F theta, which is G mod P theta. So now, I mean, I'm suggestively adding a theta that reminds the subset of roots that I had before. But so there are, as always, three different ways of thinking about this. One of them is like my favorite one, which is this cat0 perspective, geometric perspective, Riemannian geometric perspective, in which G mod P theta is the stabilizer of ray. So I take a vector V in my Weil chamber, and I look at this geodesic radiated spans, and then P theta is stabilizer in the visual boundary. So this is a subgroup of G, because G is acting on the boundary, and this is a special subgroup that has a compact quotient. And actually, all compact quotients of G arise this way for some choice of P theta that you can see in the boundary. Another way of thinking about this, so this is like the more Riemannian geometric way of thinking about these objects. The more linear algebra, linear algebra way of thinking about it, that's why it's called flag manifolds, is because these are very often flag of subspaces with some properties. For example, in for example, if I take SO PQ as my group G, then F theta is all sets of the forms Li1, Lik, such that Li1 is a vector subspace of Li2, which is a subset of Lik. So these are linear subspaces, which is a subset of R PQ. And Li is isotropic. So if I was taking SL and R, which is the standard example, I would like F. So and here theta is the set of I1 up to Ik. So the roots of natural names, and this is maybe alpha I1 up to alpha Ik. So I choose is a subset of 1p. So the roots, the simple roots of SOPQ are in correspondence with the integers between 1 and p. And a subset is a choice of such integers. And the corresponding flag space is flag of isotropic subspaces of those given dimension that are one inside the other. And here I'm always assuming that when I write SOPQ, I assume without loss of generality that p is more equal than q, and I really want p strictly smaller than q for this to work. Thanks. For p equal q, there is a similar description, but it's more complicated, and we'll swipe it under the rug. Yeah? So like, and my idea is that I want this to be the boundary I'm looking at, rather than this one, because this is really G-homogeneous. So it's the better place where to work and to get properties. So I told you, like, I have this f theta that has these properties, and there is also a more Lie theoretic way of defining it, but maybe I will not tell you. And but to pass from, yeah, maybe I should still tell you here that if I want, like, if I have a vector v theta, I have a vector v in A plus. This gives rise, as I was telling you, to a parabolic subgroup p theta in G, and thus to a flag manifold f theta, which are all the vectors at infinity conjugated to v infinity. And now what is theta? Theta is going to be delta minus the set of alpha in delta such that alpha of v is equal to 0. So if I am in the center of the Weil chamber, nothing vanishes, and so I have the whole delta. If I'm in here alpha 1 is equal to 0, and so theta is that parabolic. More generally, I will have more complicated structures under the pendulum. No? Any questions on this? Okay, and we will. I want to look at the definition, boundary map as boundary map for representation rho from gamma to G is a gamma equivariant map phi from the boundary of gamma to G mod p theta. And I will call maybe this a theta boundary map. And I really think of this as starting, so like here I have the boundary of gamma, which is really the circle for what I'm interested in. And this boundary map is going to go to some weird, still homogeneous, still an algebraic variety, but it's G mod p theta, and it's going to trace some object in here. This is what I mean about boundary map, and now the theorem is going to ask about extra property. Right? So.
Have you written down how phi is defined by rho?
No, but being now I'll start adding some adjective, and I will tell you that this is uniquely determined, essentially, by rho. Yeah? And maybe let me say here that a boundary map, so like on G mod p theta, if theta is invariant under the opposition involution, there is a natural notion of transversality. Maybe in G mod p theta cross G mod p iota of theta, which are going to be the same object for what I care about, since I'm asking that theta is invariant under the opposition involution, there is a notion of transversality which you can think of in 3 terms. The first one is in terms of linear algebra, meaning that this means that these things are really transverse. And in this setting, for example, you ask that Li1 is transverse not just to the new guy of the same dimension, but even to its orthogonal. But there are ways of phrasing transversality as transversality of subspaces, which is like can be phrased as transversality of subspaces can be equivalently reformulated as asking that to be in the open G orbit, or asking that there is a geodesic gamma from R to my symmetric space such that gamma of infinity is P1 and gamma of minus infinity is P2. Meaning that a pair, or maybe I should call it X and Y, is transverse so I take 2 points X and Y in this flag space that I assume that P theta is equal to P involution of theta, and I want that in the symmetric space there is a geodesic that goes from this point at infinity to the other point. What I wrote here is that I can talk about transversality for 2 points in G mod P theta and G mod, still P theta under my assumption up there, and equivalently are transverse is if they are transverse as linear vector spaces or flags of subspaces, so that whatever can be transferred is transverse. Or equivalently, I have a G action, diagonal G action on these pairs, that there is a unique open G orbit that's dense. Being in there is a Lie algebraic way of saying that they are transverse. Or the Riemannian geometric way of saying they are transverse is that I find the geodesic in the symmetric space that has one and the other as endpoints. This is when I think of G mod P theta, where was it? Inside the boundary at infinity. Yes, so this is some visibility property. In rank 1, this all means they are distinct. In higher rank, there are many more complicated possibilities that make the geometry of flag spaces very rich and very interesting, and allow for a bunch of interesting construction. Yeah? Okay, so the theorem on which I wanted to finish, if there are no questions on this, the theorem on which I wanted to finish yesterday, due by the same people in this generality, is that, let me write KLP BPS, so this orders here, is that if rho is theta Anosov, then it admits a continuous equivariant transverse boundary map. Boundary map that I call phi from the boundary of gamma to G mod P theta, which is what I was calling F theta. Yeah. So like, as in the case of 2 different hyperbolic structures, I want to have a map at infinity. I want this to be equivariant with respect to rho, meaning that if I act with gamma on the left, and I do phi, or if I do first phi and then I act with rho of gamma on this flag space, I get the same thing. So this is what equivariant means. Continuous means I have a topology in both cases, and I want this to be continuous as a map. And transverse means that for any pair of points here, x and y, that are distinct, the image in this flag space is are transverse. So I have phi of x here, phi of y there. And if I think of this flag space as something sitting in the boundary at infinity of the symmetric space, I actually have a geodesic inside that joins it. Yeah. Okay? Yes? There was a question? Yeah.
Yes, so if I'm not mistaken, at the start, since delta gamma is hyperbolic, all the points are transverse, right? Like
yeah, all distinct points are transverse.
So I guess that means that the image is all in the like one.
Every pair is in the like if you look at the boundary cross boundary minus the diagonal, it will all land in the open G orbit. That's what this means.
So say in one.
Yeah, in the only big G orbit in there. Like in these, here you have one G orbit that's open and dense, and then you will in these pairs of points at infinity, which here is really this transversality, and then you'll have more complicated positions, which is maybe it's not quite transverse, but like I mean I have a flag of 7 subspaces, and the second is not transverse to the second, everything else works fine. This is one example of one of the possibilities. You have lots and lots of orbits. Like they grow they grow exponentially in the rank. I mean, relative position. Okay. As to get back to the question that I had before, asking for continuity and equivariance means that if such a map exists, is unique. Why? Because the set of fixed points in the boundary is dense, and if it's continuous and equivariant, every fixed point needs to be mapped to the attracting fixed point. Right? Every element has a single attracting fixed point in the flag space, which in the SLD is really like the G is an element of SLDR, then G plus in F delta. So like to give an example, I take the flag with respect to everything. This is the eigenspace for lambda 1 containing the eigenspace for lambda 1 plus lambda 2 plus the eigenspace of lambda 2. Right. So like if G belongs to an SLD and it's regular, like is diagonalizable with distinct eigenvalues, then I have my fixed point, which is I take the top eigenspace, and then I take the eigenspace for the top 2 eigenvalue, and I go on like this, and this gives me a point. And it's the only point in this flag space where everything gets attractive. And that's what, yeah. And essentially, in very many situations, asking for continuity and equivariance means that the attracting fixed point has to go to attracting fixed point. And then by density, we know that if this map exists, it's that map. And so it does not always exist. Typically, this map parametrizes the minimal invariant subset of this flag manifold, which very often is not a small circle. Very often it's a big set, so it's no Anosov representation. But in case of Anosov representation, I really have a circle in here, or something homomorphic to the boundary of gamma, which has this strong property. Because in higher rank, being transverse is really a condition. It's not just being distinct. Okay. Any questions on this?
Is there any situation in which the map has high regularity?
Yes, this is a very good question. And in the settings in which I'm going to talk about, this map has high regularity. It's a theorem. These are theorems, but I'll tell you later. So in general, it's not, like in general, for example, so these maps are always holder. And in general, you cannot ask for more than holder, because on the boundary of the group, there is not more structure than holder structure. Like 2 different hyperbolizations up there will differ just by holder map. So that's the only not intrinsic structure that I can put there. But it is true for the case that I will tell you later, like this, for the from the second lecture, I'll talk about this theta positive representation. And for those, the boundary map, the image of the boundary map is either a C1 submanifold or at least a Lipschitz submanifold, which is a very nice, very rare property. Even in, I don't know, SL2C, you get really Holder fractal object with higher Hausdorff dimension. More questions or comments? So if not, let me tell you a little bit about, okay, so this is, so this Anosov condition is a very restrictive, but still rather general condition that holds for many subgroups of Lie groups. And we have a lot of interesting results from very different set of flavors about Anosov representation of dynamical interest, of geometric interest, and like, it's a very active field and we know many interesting properties. And in general, these are open subset of the character variety. And what I wanted to tell you in this mini course are special classes of Anosov representations of fundamental groups of surfaces for which these are also closed. And this means that they fill up connected components, as it was in Teichmüller space. And somehow, if, like something I didn't say, is that the Anosov representation in rank 1 group are convex compact subgroups, if you know what those are. So the theory of Anosov representation generalizes convex or compact subgroups in high rank. This theory of theta positivity, which is like the topic of my second lecture, really generalize Teichmüller theory, so really generalize holonomies of hyperbolizations in high rank. Yeah? And the reason why I wanted to talk to you about this is because in proving that this theta positivity has this property that I was announcing, we develop a lot of tools that might be interesting and useful also elsewhere, and maybe you can use in some places or in your research, if I get to the tools. But any questions on this? Okay, so theta positivity is a theory introduced by Guichard-Wienhard a few years ago. So if there are, like it was 20 years of Anosov representations last year, there was a conference with this title. Like theta positivity is really out since like 3 or 4 years, I think. Like the first announcement of Anne and Olivier is maybe 4 or 5 years old. And this is really a property of some pairs, Lie groups, so it's a property of flags, I mean, of flags that generalize the circle. Right? So, and what is very nice about the circle is that there is a cyclic orientation. So, like important feature of S1, say maybe among boundaries of rank 1 spaces, is the cyclic orientation. Or maybe to make it more adapted to what I'm going to say later, so this means that this is positively oriented and this is negatively oriented. Or a better way, a more adapted way to study general properties is to think that if I take A and B transverse, so distinct, so they determine 2 intervals in the circle. Like they disconnect the circle in 2 connected components, so which are called 2 intervals, I1 and I2. So let me write this. So A, B in S1 distinct, they determine 2 intervals. They disconnect the circle in 2 connected components. And this interval have nice nested with nice nesting, meaning that if I take 2 points and I take a third point now, see C will lie in one of the two intervals by definition. And C will determine, C together with B will determine two intervals, and one of them is contained in the previous. So if, meaning that if C belongs to one interval, I1 determined by AB, then there exists ICB contained in IAB. So like C determines one of these intervals, one of the two intervals determined by C is inside the previous interval. And this is very good because lets you play with the cyclic ordering and do a lot of things. And for example, tells you that sequences will have to converge. That's the monotonicity that tells you things will converge, sequences will converge. Okay. And this theta positivity is this question about theta positivity is really which flag spaces of theta have something similar. Okay. So let me give you this definition due to Olivier and Anna. Say that a family of diamonds, so let F theta be a flag manifold. A family of diamonds is a collection let me call this D for diamonds. There are triples D, A, B, where D is a subset of F theta. Remember that this F theta, I think of it as some boundary of the symmetric space for some group G. And A and B are points in F theta such that that satisfies some axiomatic. So the first property is that these points A, B, which are going to be the extremities of these diamonds, I'll explain you why I draw this picture, are in F theta but are transverse. Let me like a write X transverse to Y if one of these three conditions hold. So they are in most generic position possible in the flag space. And again, I assume here as before that theta is invariant under the position involution, so they can talk about this transversality. And so I want A and B to be transverse, and to mimic this picture, I want D to be a connected component of OA intersected OB, where OA is the set of C in F theta such that C is transverse to A. So my schematic here is that I have, so this lives in my flag space F theta. I choose one point in F theta. Typically, the other points will be transverse to A. But I will have a lower codimension locus, that's an algebraic subvariety of F theta, that are the points that are in bad position with respect to A. I take this out. It turns out that the complement of this X here that I'm drawing is a cell that's isomorphic to R to some power. But if I choose a second point B, and I take out again the things that are non-transverse to B, then as it was in the case of the circle, I'm splitting in more than one connected components. And this D is one of those. It will always be true that if I take this intersection for any flag space, this is going to have finitely many connected components, maybe just one. And I want to choose some of these connected components. Yeah? So this is the first property. I will want to have more than one to this be a non-trivial condition. So the second property is so these are like that A and B are the extremities of D. I have a family of objects like this, open, like the analog of the interval in the circle, and 2 points that determine this, or sort of determine this. The second property is some symmetry. Okay, it's not so important. If D, A, B belongs to D, then I want that also D, B, A belongs to D, which means that for some reason, I will not be able in general to say positively oriented or negatively oriented. And I want that to confuse positive orientation and negative orientation. But this is not so key. So this is important. A third property is that for any D, A, B in my family, and for any G in G, where F theta is G mod P theta, I want that G D, G A, and G B belongs to D. So I want my family of intervals to be closed under the G action on the flag space. And the third property that I want is this nesting. This is G equals 1. And the fourth, which is really the restrictive. So far I haven't said anything. So far I can always set things up like that. But the important thing that it's very rare is this nesting, which mimics what I had there, which is that for any D, A, if I start from a diamond in my family, and for any C in D, so like let me put the picture again up. So I have A, B, and my connected component D. I want that for any other point C that I find in this connected component, there exists D prime A C also in D with D prime contained in D. So say that like this was my, I started from 2 transverse points and one of the connected components in there. I want that for any other point C inside there, I can find a smaller diamond D prime that's determined by A and C, and it's nested inside. Any questions on this?
So you need to ask that there is an opposed diamond?
It's the no, it's gonna be automatic. Like this is not the opposed diamond, but it's gonna be automatic that there is an opposed diamond. And we say that a pair Are there more questions on this definition? So we say that the pair G F theta, or maybe let me call this GP theta, such that there exists a non-empty family of diamonds in G mod P theta is called the theta positive pair. And observe that by the second property, if there is at least one diamond in my family, then there are tons and tons of diamonds, because G acts transitively on transverse pairs. So any pair will bound at least one diamond. Yeah? And maybe an example is S1. Like one example is the pair SL2R or PSL2R, comma the intervals is a theta positive pair. And a known example is PSL. So this is PSL2R with P. There is only one parabolic. That's the boundary. And PSL2C with its unique parabolic is not a theta positive pair. Why? Because I have the sphere, and given two pairs of points A and B, they don't disconnect in any way. So there is no way I can get nestedness, because I have only one connected component, and that's not true. Yeah, there is no way, because A does not belong to the diamond. So I have only the connected components is only everything. There is only one possible connected component, which is everything minus A and B. And now if I put a point C, there is no nesting, because A was not in the original diamond. So there I have no choices. And the general feature is that typically you don't expect to have this family of diamonds that have these nice nesting properties. But there are some families that have been classified. And let me just maybe so the idea is that as soon as you have this family of diamonds, you can play the same construction that you can think in your head that you were in the circle and you had this interval and this nesting in intervals. And these allow me to tell you what are theta positive representations. Let me just, like I wanted to have another example that maybe you can see as an exercise. If I take SO to P as a Lie group, or PO to P, PSO to P, yeah. So that preserving a formal signature 2P, and I choose F theta to be the set of isotropic one-dimensional subspaces of R2P, then there is a family of diamonds. And there's the picture to like hint the exercise that maybe was not in my exercise sheet because I was hoping of doing this in class, is really this, the picture. So like if you take isotropic one-dimensional subspaces, then there is a natural form of signature 1 P minus 1 on this space. And you can take the future and the past. And this gives you the set of positive triples. So like local, you have some things with cones. And you have nestedness of these things.
Here the negative index is 2.
Huh? Here I have 2 and P.
Yeah, but which one is a negative 2 or P?
It's the same. Like I always assume that to me, like to get my notation before, I would have 2Q. And I think of 2 as positive and Q as negative. Okay. But this is really non-relevant. Okay. Because I can just take minus everything and I get the same object in the same group.
That P is greater than 2.
I assume that P is greater than 2. P is greater or equal than 2. I mean, if P equal 2, there is still true, but it's S1 equals S1. Thanks. Okay. So I'm already late. Okay, let me just take 1 minute to say what, so like, let me say, like if F theta admits a family of diamonds, So in this case, we say that in n tuple a0, an in f theta to the n plus 1 is theta positive if there are nested diamonds di, ai, an. So meaning that. So I started from, I have a0, I choose a diamond d0, I choose a point a1 in d0, then I have a diamond d1, and I have a2, and so on and so forth. So this is the analog of being cyclically oriented. And we say that if G p theta is a theta positive pair, we say that a representation rho from gamma, which is the fundamental group of a surface, to G is theta positive if it admits an equivariant positive map, which means that maps positive n tuples, which is cyclically oriented n tuples in the circle, to positive n tuples, n plus 1 tuples in G mod p theta. Yeah? So this is the analog. For these cases where I have this diamond nesting, this is the right analog of being monotone for the boundary maps of hyperbolization. Yeah? So like so in general, the pairs of groups flag space that are theta positive pairs is classified. There are 4 families. And the theorem that we proved with Jonas Beyrer, Olivier Guichard, François Labourie, and Anna Wienhard is that theta positive representations form connected component of character variety. So in particular, they are closed. Labourie-Guichard-Wienhard proved that they are necessarily Anosov, that this implies that the representation are Anosov, and we proved that also implies that it's closed in the character variety, so they really form connected components. And the hope of my next 2 lecture is to give you some tools that we developed into showing that these theta positive components are closed, or these theta positive representations are closed, which I think might be useful elsewhere in the study of representation dynamics. Question?
What do you mean by equivariant positive map?
Yeah, that I said, but not right for the lack of time. But the idea is that, so equivariant means that it's a map. Sorry, maybe I should have written what this is. So this is a map, as before, phi from the boundary of gamma to G mod p theta. And I told you that the boundary of gamma has a positive structure, which is the cyclic ordering. And what I want is that if I have an n tuple that's positively oriented, this gets sent to an n tuple that's positively oriented. In general, if this is really the fundamental group of a surface, enough to check for triples.
Sure.
But this works very well also for fundamental groups of surfaces with boundary, where I have a Cantor set with an ordering. And in that case, you need to check on quadruples and not on triples. More questions or comments?
Are positive maps automatically continuous?
If it's not a free group, yeah. Yes. It's automatically continuous and automatically dynamics preserving. Yeah.
SL3R is not positive, right?
SL3R is positive with respect to the full flag space. This is one of the exercises. One of the exercises is to understand what are in the full flag space for SL3R. You can figure out there are 6 connected components, like a pair determines 6 connected components, and 4 of them are good, and 2 are bad.
Do any complex groups admit positive pairs?
No, also because like if you look at the adjoint form, the character variety will be connected then, and you will have always the trivial representation. So as a result of our theorem, this is never the case. There is also the classification that I could write on the board of the groups admitting a positive pair.
Will you give the classification of all the positive of the theta positive pairs?
Yeah, I can write it on the board like tomorrow just before class, and we can comment on that.
But is so a product of G, I mean, a product of groups admitting a theta or pair is again positive?
Yeah.
With respect to the product of the
everything is splits.
So I'm assuming this notion has no analog for non-Archimedean groups because you use this connected notion?
I mean, so like there is an analog notion for non-Archimedean groups, but like you can make this work very similarly, but admitting in or group fields with an ordering. So this is like no local fields admit an ordering that's compatible with the field operation, but there are these big Robinson fields that do admit an ordering that's compatible, and there are also like real closed fields that are much like finite transcendency degree extension of R. And for those, there is a very nice notion. And this has been studied, or is being studied by like me and collaborators, and also like Xenia and collaborators. If there are no further questions, I guess we go for a picture, or?
Let's clap first.